Hi everyone. In this video we are going to focus mainly on solving problems related to enthalpies of reactions. I will also introduce a new term, specific heat capacity. Actually, this is the first video where we are going to discuss this reaction or this equation right here, Q equals mCs delta T. But before we get to that equation, let us remind ourselves about enthalpy. So enthalpy of a reaction, or delta H, we learned an equation a couple of videos ago. Delta H of the reaction equals Q of the reaction divided by moles of reaction. So this is the amount of heat released or absorbed per mole of cycles of a reaction. And don't worry, we'll discuss more about this odd term here. Just remember though, this delta H equals Q business, that only happens at constant pressure. But that's fine because most of the reactions that we're going to look at occur at constant pressure. So this is very usual. Because the reactions are done open to air. They are not confined to a volume, usually. Okay, let me give you a reaction. It is going to be an exothermic reaction. We have N2 gas plus 3 molecules of hydrogen gas mix ammonia, 2NH3 gas. And the delta H associated with this reaction is negative 91.8 kilojoules per mole. And that is mole of reaction. So let me put how it's read. It's read negative 91.8 kilojoules per mole of reaction. So mole, Avogadro's number, 6.02 times 10 to 23. When this reaction runs that many times, it's going to give us release 91.8 kilojoules. But we could also think of it as this, and I would like for us to think of it like this. The reaction releases 91.8 kilojoules for every 1 mole of N2 used, for every 3 moles of H2 used. I'm getting it just from the coefficients, and this is much energy is released for every 2 moles of NH3 produced. Okay, so that's how we're going to read this when it says per mole. Okay. Keep that in mind. Let us do a couple of problems. The first problem looks like we are figuring out the amount of energy required for a reaction. Oh, let me write here that we're going to look at 2 problems. Right, if you want to copy this, this is example number 1. You could pause the video, obviously, and then see if you can answer how much solar energy, or you could just think of it as how much heat because heat is going to be identical or equal to enthalpy. How much heat is required to produce 75.0 grams of, this is glucose. So glucose is the solid here. So before you pause the video to attempt this problem, let's just figure out the lay of the land right now. Delta H is positive, so this is endothermic. The heat term is as at the beginning. They want grams of this. Well, they don't want grams of this. They want to produce 75 grams of this by adding some energy. Now, looking at the coefficients, if this much energy is added into the reaction, I would expect 1 mole of glucose and 6 moles of O2 for this much energy. And that mole of glucose corresponds to a gram of glucose. All right, but I really want 75.0 grams, so we're going to work backwards. Hopefully that was useful. I'm not 100% sure that was useful. I'm going to shut up and give you time to do this problem. Go ahead and pause the video. All right, we're back, and this is what I would do for a problem, for almost all the problems. I want to identify what the grader is looking for. The grader is looking for energy required. So here's your question mark, and probably I'm going to give it in kilojoules. It has to be an energy term, an energy unit. All right, and we are given 75.0 grams. I'm going to do this via dimensional analysis or via unit canceling. So again, they want energy required. That tells me that's endothermic. This is plus. So this is endothermic. And you could literally write the word heat at the beginning. Heat added. The target is kilojoules. Good. And I'm going to read. So remember from our notes, where are they? Here it is. For this number here, we read it per coefficient mole of each reactant and each product. But this is easy because this is coefficient of 1. So that is the amount of energy needed to make 1 mole of this. All right. So I'm going to read it as per mole, not of reaction now, but per mole of, this is again glucose. So here's the math, and it's in blue. 75.0 grams. I know I need moles because I could convert moles eventually into grams. So here are your grams. And I have this many moles. Did I misspeak? I want moles because I could convert that moles into an energy term. So I take those moles. So it's not 1 mole of glucose that I'm trying to form. It's actually less than a mole. So I would expect less energy required. Take those moles, multiply it by the enthalpy. Look what I'm canceling out, and look what's left over. Kilojoules. And then I round to 4 significant figures. 1,167 kilojoules. That's your answer. Okay. Again, I really rely on unit canceling or dimensional analysis to get the units that I want. Okay. Next one might be a little more tricky because, see, I don't have any. Oh, I have O2, which has a coefficient of 1. But you notice here that they want the mass of copper, grams of copper. So if I need grams of copper, I probably need moles of copper. But for every mole of reaction, I produce 4 moles of copper. So there's my conversion. This is how much heat is needed to get 4 moles of copper. So they started off with the amount of energy that is added, that is consumed. So the heat goes here, and I need to convert that heat into moles. and then I'll convert those moles into grams. But the tricky part is you're producing 4 moles of copper for each cycle, for each mole of cycle. Again, I don't know if I'm confusing matters for you. Go ahead and take a moment to read this on your own, and then do this problem, and we could compare answers. Okay. I always do the same thing. I try to identify what is needed, and mass is needed, and I'm going to assume, well, I'm going to figure it out in grams first. All right. I may change it to kilograms if it's a large number. You're given amount of heat consumed. Oh, so this is endothermic again. Let me use purple. Endothermic. And that amount of heat is at the beginning. Heat plus. Good. So we're adding heat to drive the reaction. All right. So now when I'm reading, let me focus again. Okay. As I read this number, I think of moles per reaction, or this is the amount of energy needed for every 2 moles of copper 1 oxide, for every 4 moles of copper produced, and for every 1 mole of O2 produced. And I'm more interested in the copper. So that value I'm going to read as 333.8 kilojoules for every mole for 4 moles of copper. So that is the conversion factor that I am going to use. Start with what's given. Start with I like to call it the data, not the conversion factors, but the data right there. I got to get rid of kilojoules using enthalpy. So it looks like I took the inverse to make sure the kilojoules cancel. But there's an important number right there. It's not that many per molar reaction. It's this much energy per 4 moles of copper. At this point, you have moles multiplied by the molar mass of copper. And yeah, the grams is pretty high. So I'm going to move the decimal place 3 spots to the left to get kilograms and round to 3 significant figures. 3 significant figures. Okay, just try to keep your wits about you. There's no really equation, right? There's no boxed equation that I use. It's how to think about the problem. And most people, not most people, but some people really understand, oh, I add this much heat, I produce this many moles. For me, I like to start with the data, understand what the last unit should be, and use dimensional analysis for me to figure out, like, is it moles over kilojoules, or should I use kilojoules over mole? Well, in the first step you gotta cancel out kilojoules. So I took the inverse of this value. Okay, let us go back to the notes because I do want to talk about this specific heat capacity. A new topic, but very, very related because we're still dealing with heat. And this is, well, I'll give you the definition right now. Specific heat capacity. What's that sound? Okay. This is the amount of heat needed to raise the temperature of 1 gram of substance up by 1 degree C, or degree K, same difference. So the symbol is CS, C subscript S. Sometimes online or the textbook, they don't write this S. And that is in, what are the units? So it's the amount of heat, there's your energy term, divided by a gram per gram dot degree C. And so this is degree C is a difference. It went up 1 degree. So that the difference is final minus initial, and the final temperature is 1 degree higher than the original. I'm going to put a box here. It's not really an equation, but it's a very important term, and we should really understand the units, especially if you depend on unit canceling or dimensional analysis like we did in the previous two problems. Now, I looked this up in Google, specific heat capacity, and Google says this is joules per kilogram dot degree C, but I'm not sure why they do that. Almost all textbooks, every textbook that I've seen, reports specific heat capacity in these units. In fact, I printed out a table that has specific heat capacities. Okay, and look at the units. All right, so it is at 25 degrees, but this degree means the difference, a difference in temperature. So this is the amount of heat needed to raise 1 gram of H2 gas 1 degree higher, degree C, Celsius. Look at the range, 14, and I didn't go all the way to the bottom of the table, but here we have 0.4, so it's very wide. And whenever I come across a new table or a new parameter, in this case specific heat capacity, it makes me feel better if I know the units, obviously, but also the range, like what is a reasonable number for a specific heat capacity. So let me pick up a couple of them. I'm not going to copy the whole table, but it'd be nice to get a feel for these heat capacities. And the most popular one that you will be using is water in the liquid form. The heat capacity for that is 4.184 joules per gram dot degree C. But it's going to be different, for instance, water in the solid form, for ice. This is H2O solid form. That specific heat capacity drops. It drops to 2.010 and same units. All right, so water, liquid is 4.184. Something that's very high, we saw that H2 gas, and that is 14.267. All right, so what are some other interesting substances? Like, did you know that, I don't know, air has a specific heat capacity? Air is 1.020. What about some building materials? We have aluminum, concrete, and glass. And they're actually pretty similar. Concrete and glass, let's do those two. And concrete is 0.880. And then glass is very similar, 0.840. Again, so water needs more heat to raise it 1 degree higher than air, than concrete, than glass. For these three, it takes less heat to raise its temperature. So do you see how interesting that is? To raise the temperature of the air in an oven, you need a certain amount of heat, but that certain amount of heat could heat up glass differently, right? Glass will get actually hotter because it has a lower specific heat capacity. So Q and temperature are related, but they're not equal. Okay, they're not equal. Let's take one more. Let's take a metal. Let's take nickel. And that's very low. So metals get metals feel hotter faster with the same amount of heat added as if you added the same heat to water or same heat to concrete. So that's why for me it's important to jot down a couple of values when you're introduced to a new term or introduced to a new table. One more problem and then I will let you guys go. Look at one more problem. Okay, and that problem is number 3. Again, go ahead and pause the video and copy this if you want to practice this later on your own. It's a heat capacity, specific heat capacity problem. And we are, oh, actually, I should have given you this first. Well, no, let's do it this way. Using dimensional analysis, can we figure out the amount of heat required to heat? So we are using specific heat capacity. We're adding heat to raise the temperature of some mass this many degrees. But it's not 1 degree, right? It's not per degree, it's the difference now. So we have to raise it, I don't know, what is this? 65 degrees? Is that right? Around 65 degrees. So we're going to multiply the delta T by this number to get rid of the degrees C. Ultimately, we want joules that will convert to kilojoules. Some of you know the equation that this is referring to. I haven't introduced it yet in this video. When I do this problem, I'm depending only on dimensional analysis because I want to show you the power of dimensional analysis. Even if you don't know any equations, you could most likely figure out an answer that gives you the right units. All right? Pause the video, and when you have an answer written down, come back. Okay. We're going to use the power of dimensional analysis, unit canceling. And so I have these terms. I have grams, I have degrees C, and actually this is really delta, final minus initial. Final temperature, this is the initial. So delta temperature is going to be positive. And I'm given the heat capacity, specific heat capacity, and with these units. Start with some data, 255 grams. So when I multiply that by the specific heat capacity, I'm able to get rid of grams, because my goal is to get joules. And then when I multiply this by the delta T, I get rid of Celsius, and I'm left with joules. So the joules is pretty big. I'm going to convert it to kilojoules by moving the decimal 3 places to the left. So I mentioned that some of you may know what equation I'm using, an equation that I have not yet written down. That equation that we were able to derive by dimensional analysis is mass, specific heat capacity, delta T, the amount of heat. So this is the last thing I want to say for this video. It's a box equation. Q equals mcs delta T. Again, sometimes people don't put the S. That's perfectly fine. Those of you who are have aspirations of being a doctor, you know you're going to take the MCAT. So a lot of my students say this is Q equals MCAT. Okay, because they pretend that this delta is in the letter A. Whatever it takes, guys. Okay, I will see you in the next video. We're going to use this equation a lot in problems that are called calorimetry problems.